Hi everyone, welcome to the next video. In the last video we were looking at the derivative of the exponential function. In this video we're going to be looking at the integral. Okay, so when we take the integral of e to the x dx, remember that the derivative of e to the x is also e to the x. So once again the integral is also going to be e to the x and then plus c. Now if this exponent is a u, right, then e to the u du, if the u is something other than just x, then it would be e to the u plus c. Now, keep in mind, I'm going to put a little star here because the du has to be satisfied. Remember u substitution, the du has to be satisfied before you can integrate. All right, so here's an example. On this one, it looks like we've got a whole lot of letters, and we do, but let's rewrite this in order. I have e to the negative x squared 3x dx. Okay, so I'm just reordered it. So we can see that the u is going to be the exponent, which is negative x squared, and so du is going to be negative 2x dx. So I can see here that I don't really need the 3, so the 3 can come out, right? I'm going to write it like that. And then I have e to the negative x squared, and then I have x dx. Well, because this is the u, I need the negative 2. And then multiplied, I need the negative 1/2. All right, so now that the du is satisfied, by putting the negative 3/2 on the outside, then I would have negative 3/2 e to the negative x squared plus c. Okay, so on the next example, I'm going to go ahead and rewrite this. I'm going to have the integral of e to the 2 over x, and then 1 over x squared dx. Right, so u is going to be 2 over x, which is 2 times x to the negative 1. So du would equal negative 2x to the negative 2 dx, all right, which of course is negative 2 over x squared. All right, so I'm looking up here, notice that right here. So you notice that I have a negative 2, but I have a 1, so that tells me that I need to add a negative 2 here and a negative 1/2 out here. So when I integrate, negative 1/2 e to the 2 over x, because I've satisfied the du, plus c. So this works for definite integrals as well. And so we look at this, it looks like we've got a 1 over u situation. So I'm going to let u be the denominator, 1 plus e to the x. Du is going to be e to the x dx. So if I rewrite this, I've got 1 over u, and then e to the x dx is du from 0 to 1. So that's going to get me the natural log of u, which is 1 plus e to the x, and I want to do that from 0 to 1. So I have the natural log of 1 plus e minus the natural log of 1 plus e to the 0. Careful, because that's 1. So this is the natural log of 1 plus e minus the natural log of 1 plus 1, so that's 2. So I could write it like this using the quotient rule, the natural log of 1 plus e over 2. And if you throw that into your calculator, that's going to be approximately 0.620, because remember, 1 plus e over 2, those are all constants. So for the next example, you can see again that it's probably out of order, but we're going to go ahead and write this. I'm going to just change up the order a little bit. I'm going to say cosine of e to the x times e to the x dx. And then I'm doing that from negative 1 to 0. All right, so that's going to mean that u is e to the x, and du would be e to the x dx. So the du has been satisfied. So I'm going to go ahead and the integral of cosine is sine. So I've got sine e to the x from -1 to 0. So that's going to be sine e to the 0 minus sine e to the -1. Well, e to the 0 is just 1, so I have sine of 1 minus the sine of e to the -1. And so that's just a constant. So if you, we could write it the sine of 1 over e if you just really wanted to, but these are not logs, so you can't put them together. So when you throw that in your calculator, you're going to get 0.482, rounded to 3 decimal places. This is one of those problems that looks really hard, but if you think about it and use substitution, it's really not that bad. So we're going to let u be the denominator, because we might be able to use natural log. We'll see what we get. When we take the derivative of this, we're going to get e to the x minus e to the negative x times -1. So we have something that looks like that. Well, that looks like the numerator, dx, does it not? So let's rewrite. We've got 1 over e to the x minus e to the negative x times e to the x plus e to the negative x dx. Okay, this is du. This is 1 over u, right? This is an indefinite integral. So I have the natural log of u, which is e to the x minus e to the negative x plus c. So that's one of those that just looks really hard, but not that bad. E to the x is really easy to take the derivative and the integral of. So here's the same. This is an integral problem, but this is the one that threw us, a lot of us, on the last test, just because of the way it was written. All right, it says find the area of the region bounded by the graphs of the given equations. So y equals x times e to the negative x squared divided by 4. Y equals 0 is the x-axis. So we want the area bounded by the function, the x-axis, and then the vertical lines 0 to square root of 6. So we're going to write that as an integral from 0 to square root of 6 of e to the negative x squared over 4 times x dx. I'm going to let u be the exponent. So negative x squared over 4 du is -1/2 x dx. Right, so that means I'm going to add this -1/2 here and -2 here. Once I do that, then the integral is just going to be -2 e to the negative x squared over 4. I'm having trouble with that 2. Hopefully you can tell that it's a 2. From 0 to square root of 6. All right, so we just plug it all in. So we have 2e to the negative square root of 6 squared over 4 minus -2e to the 0. Okay, so that's going to give me, if I look at this first part, that's going to give me -2e to the -3/2, right? Because this would be square root of 6 squared, which is 6, over 4, which is 3/2, plus 2, e to the 0 is just 1. And when you put that in your calculator, you get 1.554. Okay, so I hope you've paid special attention to all of these examples. We're going to do others that are like that in class. The thing I really like about these the most is that they look really difficult, but they're really not. If you just pay attention and stay organized, they're really not that big a deal. So I will take good notes, I hope, and I will see you in class.